Hey everyone, and welcome to Atomic Theory and Structure. We're going to do part one here, talking about the history of the atom. And here we go. Let's start out with a quick little video link here about it, maybe give you another view of what's going on with this guy.
What do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize-winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question: what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom, a fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
All right, so that's a good visual of what we're going to talk about. Now, a lot of those things that were in there may have been slightly confusing because we haven't really gotten to that part yet, and that's okay because that's what we're doing right now. All right, so Democritus, okay? Democritus is kind of the father of the atomic theory, okay? He can be known, and he had this word atoma, okay? His big thing was atoma, which was Greek for indivisible. And indivisible is just a fancy thing. If you think about like the Pledge of Allegiance, the United States is indivisible, all right? It means it can't be divided anymore. Okay, it's as low as it goes. Okay, and he used a mortar and a pestle and a mortar. That's kind of like a bowl with this like clubby looking thing that they use to grind up stuff. Because we're talking about 460 BC, way back. Okay, way back. All right, atoma. Okay, atoma. All right, then there came John Dalton, like they talked about. The biggest thing we need to remember about John Dalton is this was his model of the atom. It was just literally a ball, but the ball was perfectly elastic. Okay, and what does that mean? You need to think he thought that basically atoms were like, okay, bouncy, never spell it right, bouncy balls. Okay, he basically thought that atoms were like bouncy balls. Next came J.J. Thomson, okay, JJT as we like to call him, okay. He basically, he did two huge things. And the one thing he did is he discovered what we call the electron. Now, electrons, we tend to use e to the negative 1 as the symbol, okay, so electron. His experiment that he used, okay, was with magnets. Okay, magnets and what we call a cathode ray tube. Okay, a cathode ray tube. Okay, he was looking at gases and things under pressure and under stress. So from that, he develops what they call the plum pudding model. Okay, in the video you just watched, they called it like the chocolate chip cookie model. Okay, so this is still JJT, the guy before here, this guy over here. All right, so again, we need to know the term plum pudding model. Okay, they use the term chocolate chip cookie, but the idea is if I was to take said chocolate chip cookie and I cut it into pieces, is every piece going to look the same? Okay, we have no idea. I also like to think of like a blueberry muffin. You open a blueberry muffin, you know there's blueberries in there. We knew there were electrons inside the atom, but where are these electrons? We don't know. So plum pudding is literally a dessert that used to be served in England and things like that. All right. So the biggest thing is then we get to Ernest Rutherford. His huge thing is this thing called the gold foil experiment, which we're going to talk about and we're going to do a lab about. And the biggest thing that you need to understand is almost all of them go straight through except 1 in 10,000 came straight back. Well, what do we mean by came straight back? Well, let's take a look right here at this experiment.
So let's say you have to read an incredibly...
After the ad, I guess. Here we go. There we go. Good golly. All right, so here comes our alpha particle emitter. What's going to happen is it's going to fly through these little screens to kind of filter out anything else that was going on. And what happens is the little beam of light, or the alpha particle ray, is going to shoot through here. Here we go. It's going in there. That's our element, our radioactive element. All right. Fast forward here. All right, here comes the alpha particles. The alpha particles come and hit the screen, kind of filters them down into more of a direct beam. It goes through there, that last little slit, and then it hits the gold foil. Okay, and as that gold foil gets hit, a lot of them come right through, and some deflect at little angles there. Those are these little angles coming out there, if you notice. But then right there, every 1 in 10,000 right there came right there. It moved right there. Okay, and that's what we say when we say come back. So if you notice, a lot of them come straight through, and then every once in a while we get one that deflects straight back. Okay, so that's when we talk about coming back. 1 in 10,000 come backwards. All right. So again, if you're in class, we have this. It kind of just takes you back. There's more of a like cross-sectional view. And remember, what we're talking about here is that almost all of these alpha particles come straight through. All right. A few of them deflect because of there. And every once in a while, we get one that came back. And what that ended up telling us was one major, huge discovery. What that made us come up with is that there is a central nucleus, or that an atom has a center, and that this center was positively charged. That's huge. And then we get to probably the one that we're going to focus more than anything in this class, and that is Niels Bohr. And Niels Bohr, he went to the University of Manchester, okay, but basically he said that electrons orbit in shells, like planets orbiting the sun, with each orbit able to contain a certain number of electrons. That is huge. Not only did he say that they orbit like the moon around the Earth right there, like this is hydrogen. This is the central nucleus in the middle, the green part, and then you have the actual electron orbiting around like this. As you get larger atoms like fluorine, which has 9 protons, you'll see that there are 9 electrons. All right. And that's how they move around. So again, the center of the atom, you think of it like a planet, and you think of the outer parts as moons, or if you want to think of it as that middle part is the sun, and that's the solar system. But there's only a certain amount. And in the Niels Bohr model, there's 2 in the first, and then 8 in the second, 8 in the third, and we'll get to that. So we are going to do a little recap thing, and then we are going to do a lab. All right, we're going to do a lab on this. So I hope you enjoyed this. Thank you. And here we go. That was part 1, atomic history, or the history of the atom or atomic structure.